Let's now continue with Fermat Theorem. We see the proof of Fermat Theorem here in the slide on the right, and we have seen the proof last time. It states that a at power p minus 1 will be congruent to p to 1 mod p whenever p is a prime. Let's take some examples. Interesting small prime, it's 11, so the exponent would be 10. Let's take as an example 2 at power 10. It's equal with 1024, which mod 11 is going to be 1 times 2 times 4, which is 4, minus 1 times 3, 2, which is 3, so it's going to be equal with 4 minus 3 equal to 1 mod p, which is mod 11. So congruence is mod 11. Okay. So this is confirmed. We can learn from this that it will be true for any other value, like 6 at power 10 will also be equal to 1 mod 11. That will hold even for larger values, like another prime, it's 1009, so we can infer that 5 at power 1008 will also be 1 mod 1009. Another prime, it's 2027, so any other number like 21, a number different from 0 and 2024 at power 2026 will also be congruent to 1 mod 2027. We can also compute more complex exponentiations using Fermat, so we can simplify some exponentiation, which is very important for the big computations that are used with cryptography. One such example, it's let's say 6 at power 2020. We can notice that 6 at power 2020 mod 11 is congruent with 6 at power 202 times 10, which is equal with 6 at power 10, everything at power 202. This was 10, which is congruent. First, the 6 at power 10, we have seen that it is congruent to 1, so this is congruent to 1 at power 202, which will be congruent with 1 mod 11. We should certainly be able to do even more complex operations, like 6 at power 2022. Okay, we notice that we can write this one as 6 to the power 2020 plus 2, which is congruent to 6 at power 2020 times 6 at power 2. We have seen the 6 at power 2020, it's congruent to 1, so you can just replace it with 1, remains 6 at power 2. which is going to be 36, which mod 11 will be 3. Mod 11. Okay, we can similarly make any other complex computation, mod a prime. Let's still stay with 11. If somebody would want to compute 5 at power 1033, let's say, mod 11, you could write this one as 5 at power, we check 1033 divided by p minus 1, which is 11. We are still in mod 11 in this example. So divided by 10 will be equal with 1003, remainder 3. So we are going to write it as 5 at power 10 times 103 times 5 at power 3. As a reminder goes here, and the quotient goes there. So this is going to be equal with 5 at congruent with 5 at power 3, because 5 at power 10 will be congruent 1. Okay, so this is going to be all the way equal with 125, 125, which mod 11 will be 1 plus 5 is 6, minus 2 is 4. Right? So these are some ways of using Fermat Theorem for performing fast exponentiations. It is possible to do it when we work modular prime, and notice we had a conditions, the basis had to be different from 0 and any multiple of the prime number. So here 5 was bigger than 0 and smaller or different than 11. What would happen with numbers that are multiple of 0 of the prime number p, of 11 in this case? Well, Fermat Theorem has a generalization. So if until now we have seen that Fermat Theorem was written as a at power p minus 1 congruent with 1 mod p. If we decide to multiply this with a on both sides, this bar, remember, stands for multiplying both sides of a relation with the operation shown on the right. So in this case, multiplication with a, we are going to obtain a at power p minus 1 times a, it's a at power p, congruent with a mod p. What can we notice about this relation? Obviously, it is true if a is not a multiple of p. What happens if a is a multiple of p? In that case, we notice that we are having kp at power p on the left hand side, which will be mod p congruent with k at power p times p at power p. P at power p mod p will be equal to 0, and on the other side we have a, which is k times p, which is also congruent to 0 mod p. So what we can notice, in both cases we end with 0, therefore the equality still holds. So we have proven this generalization of Fermat theorem that says that whatever A if P prime, so whatever A in C, if P prime, that P A at power P will be congruent with A mod P. More than this, another way of writing this relation would be to say that P divides A at power P minus A. Right, and subtract this A in both sides, and this means that A at power P minus A is 0, so it's a multiple of P mod P. Let's see some examples. So if, for example, 3 being the A, let's work mod 5. 3 at power 5 minus 1, which is 4. It's 9 times 9, which is 81, which is congruent with 1 mod P, mod 5. We know this. If we multiply with 3 in both sides, we get 3 at power 5, because 1 times 3 equals 3 mod 5, which is obviously true and correct. And this is going to be equal even for numbers that are not relatively prime to 5, like 10 at power 5 will be also congruent with 10, which is also congruent with 0 mod 5. Okay, so the other version that we have seen over here tells us that yes, 5 will divide 3 at power 5 minus 3. We have noticed that 3 at power 4 is 81, 3 at power 5 is going to be 81 times 3 equals 243, so 243 minus 3, so 5 divides 240, which is obviously a true statement. A special case of this version of Fermat theorem is for the A equals 2, which means that 2 at any power P minus 1 congruent with 1 mod P, or 2 at power P congruent with 2, same mod P, which means that P is going to divide 2 at power P minus 2. In the case of 11, 11 is dividing 2 at power 11, which is 2048. 2048 11 divides 2046, and we notice that 2046 is indeed divisible with 11, because 0 plus 6 equals 6, minus 0 plus 4 equals also 6 equals 0, so the remainder of the division with 11 is 0. This is the end of the lecture about Fermat Theorem. Next we are going to see some application to some cryptosystems.